First law of thermodynamics. In thermodynamics, we consider a system generally an ideal gas and study its state at various pressure, temperature, volume conditions. Equation of state for an ideal gas is given by PV equal to nRT. P is pressure, V is volume, T is temperature in degree Kelvin, N is number of moles, and R is gas constant. First law of thermodynamics was propounded by Joule, and according to this law, if heat dq is given to a system, a part of it is used to its internal energy du and remaining part is used by the system to do work dw. That is dq equal to du plus dw. dq is the heat given to the system and it is equal to sum of two terms du plus dw. du is change in internal energy of the system and dw is the work done by the system. This is mathematical form of first law of thermodynamics. If at constant pressure P change in volume is dV, then work done by the system dW is equal to P dV. For isochoric process volume V remains constant, so that change in volume dV is 0. Hence work done by the system dW becomes 0, and then from first law of thermodynamics we get dq equal to du. For adiabatic process is one in which there is no exchange of heat to system and environment. For adiabatic process there is no exchange of heat by the system, that is dq is 0. Then from first law of thermodynamics we have du plus dw equal to 0 or du equal to minus dw. It is not du equal to minus du, it is du equal to minus dw. For isothermal process is one for which temperature remains constant and internal energy of the system U depend upon temperature only. If temperature remains constant, internal energy U remains constant. So du, which is change in internal energy, is 0 for isothermal process. So from first law of thermodynamics, for isothermal process we have dq equal to dw. Next topic is reversible and irreversible processes. If a process is reversed and the system undergoes through all those intermediate equilibrium states which are obtained in direct process, then the process is known as reversible process. Otherwise, it is known as irreversible process. For a process to be reversible, there are two main conditions. First is there must be no loss in energy of the system due to convection, conduction, and radiation against friction. There must not be any friction. Second condition is the process should be quasi-static. By quasi-static, we mean that the pressure and volume of the system must be changed very slowly. The above conditions are not satisfied in practice, so all natural processes are irreversible. Slow isothermal process and slow adiabatic process are example of approximately reversible process. Next topic is Carnot engine. Carnot engine is a heat engine. Heat engine converts heat into work. And efficiency of heat engine is defined as efficiency eta equal to work done divided by heat given to the system. The heat given to the system cannot be converted completely into the work. So, efficiency of a heat engine remains always less than 1. Carnot proved that it is against the nature to get 100% efficiency from any heat engine. He considered a theoretical ideal heat engine, all parts of which are free from friction and processes are very slow. Carnot proved that efficiency of this ideal heat engine can never be 100%. Carnot assumed an ideal heat engine. There is no friction. Processes are very slow. That is, processes are reversible. But this ideal heat engine is not 100% efficient. It cannot convert heat completely into work. This ideal reversible heat engine is known as Carnot engine. Following are the main parts of Carnot engine. Main parts of Carnot engine are shown in this diagram. There are 4 main parts: source of heat, sink, working substance, and stand, insulating stand. There is a cylindrical vessel which contains movable piston. piston can move up and down. All its walls are insulating except the base. Base is conducting. Heat can enter inside the cylinder through this conducting base, and ideal gas is filled inside this cylinder, which work as working substance. So working substance is ideal gas filled inside a cylindrical vessel in which there is a movable piston. Other part is heat source. There is a source of heat at high temperature T1 degree Kelvin. Its capacity is very large. If we extract some heat from it, then its temperature do not change. Other part is insulating stand, and last one is sink at low temperature T2 degree Kelvin. To obtain work continuously from Carnot's ideal engine, working substance is allowed to pass through reversible cyclic process repeatedly. In each cycle, which is known as Carnot cycle, there are 4 processes. Number 1, isothermal expansion. Number 2, adiabatic expansion. Number 3, isothermal compression. And last, number 4, adiabatic compression. These 4 processes are shown in this PV diagram. This PV diagram is known as indicator diagram. Point A, which represent state of working substance, that is ideal gas initially. Initial state is represented by point A. Here pressure is P1, volume is V1, and temperature is T1. This cylinder is kept on heat source of temperature T1 degree Kelvin. Now first process is represented in this diagram by AB. Ideal gas reaches state B from state A. This first process is isothermal expansion. Cylinder is put on heat source and piston is moved up so that the gas expands, its volume increases. This process is isothermal process because temperature is constant T1 degree Kelvin, and for isothermal process, equation of state of ideal gas is PV equal to constant. Equation of state of ideal gas is PV equal to nRT. If T temperature is constant for isothermal process, equation of state becomes PV equal to constant. And from this equation of state, we conclude that when volume V increases, pressure P decreases. This is shown in this curve AB, where volume V is increased from V1 to V2, then pressure P is decreased from P1 to P2. Temperature remains constant, that is T1. So final state B is reached where pressure is P2, volume is V2 and temperature is T1. This is first process, isothermal expansion. Now this cylinder is put on insulating stand. Now all the walls outside ideal gas are insulating. No heat can enter inside the cylinder nor outside the cylinder. So there is no exchange of heat to the system, and now the gas is expanded. Piston is moved up. Now the process is adiabatic process because there is no exchange of heat. For adiabatic process, equation of state of ideal gas is PV to the power gamma equal to constant. Here gamma is equal to Cp upon Cv. Cp is heat capacity at constant pressure, while Cv is heat capacity at constant volume. So equation of state for adiabatic process for ideal gas is PV to the power gamma equal to constant, and from this equation of state we see that when the gas expands, volume increases from V2 to V3, its pressure decreases. Now it decreases much sharply than that in isothermal expansion process. So the process BC is adiabatic expansion. Now in this process, temperature of the gas is reduced. Temperature becomes T2 from T1. Initially at point B temperature is T1, and at point C it is reduced to T2, that is temperature of sink. Other two processes are isothermal compression and adiabatic compression. CD, third process, is isothermal compression. For this process, this cylinder is put on sink of temperature T2 degree Kelvin, and now we compress the gas. Piston is moved down. So third process, which is represented by CD, is isothermal compression. Temperature remains constant, and that is equal to T2, that is the temperature of the sink, and now it is compressed, so its volume is reduced from V3 to V4. Temperature remains constant, that is T2. So finally state P4 V4 T2 is reached, that is represented by point D. Last process is adiabatic compression. For this process, this cylinder is put on insulating stand, and the gas is again compressed. Piston is moved down so that the volume is reduced further from V4 to V1, and now pressure is increased from P4 to P1. This process is done so that initial state A is reached. In this process, temperature of the gas is increased from T2 to T1. This is the complete cycle, which include four processes. First, isothermal expansion AB. Second, adiabatic expansion BC. Third, isothermal compression CD, and last DA, that is adiabatic compression. In the first process, that is isothermal expansion AB, the gas extract heat from source. It extract Q1 heat from source, let us suppose. And in the third process CD, that is isothermal compression, it is as temperature T2. When the cylinder is put on sink of temperature T2 and it is compressed, in this case the gas gives heat Q2 to the sink. Now for this complete cycle, that is not known as Carnot cycle, we want to derive expression for total work done. First of all, we calculate the work done in process 1, that is isothermal expansion. Formula for work done is W equal to integral PdV, because dW is PdV. So work done W becomes integral PdV. This work done we represent W1 for first process. So for first process, that is isothermal expansion, work done W1 equal to integral PdV, and limits of integral are from V1 to V2. This work done W1 is equal to heat Q1, that is extracted from the heat source, because in isothermal process heat given to the system is equal to work done by it. There is no change in internal energy. So from first law of thermodynamics we conclude dq equal to dw. So we have q1 equal to w1, and w1 is integral pdv. Now we calculate this integral for this process, that is isothermal process. Equation of state of an ideal gas is PV equal to nRT. In this case T is T1, so PV equal to nRT1. Substituting the value of P from this equation, we have P equal to nRT1 upon V. Substituting the value of P, that is nRT1 upon V, from equation of state of an ideal gas, temperature is T1, that is constant. So nRT1 is kept outside the integral, and inside the integral we have integral dV upon V, and it is equal to log V. Limits are from V1 to V2. If we put the limits, we get nRT1 log V2 minus log V1, which is equal to nRT1 log V2 upon V1. So this is the work done in first process, in the process of isothermal expansion W1, and it is equal to the heat Q1 extracted from the heat source, and it is equal to nRT1 log V2 upon V1. Now we calculate the work done in second process, that is adiabatic expansion. This work done we represent by W2, and W2 is equal to integral PdV. Now limits are limits of V are V2 to V3. Volume now changes from V2 to V3. This process is adiabatic expansion. Volume is expand from V2 to V3. For adiabatic process, we have equation of state P V to the power gamma equal to constant, and we write that constant as equal to K. If P V to the power gamma equal to K, then P is equal to K upon V to the power gamma. Now substituting this value of P equal to K upon V to the power gamma, this work done W2 becomes integral K upon V to the power gamma dV. K is constant taken outside the integral, and inside the integral we have V to the power minus gamma dV. Value of this integral is V to the power minus gamma plus 1 upon minus gamma plus 1, and limits are V2 to V3. So this integral becomes K upon 1 minus gamma V3 to the power 1 minus gamma minus V2 to the power 1 minus gamma. Now put K inside the bracket, and value of K is PV to the power gamma, and value of PV to the power gamma for this process BC at point B. This value of PV to the power gamma is P2 V2 to the power gamma, and at point C this value becomes P3 V3 to the power gamma. So the constant K, PV to the power gamma equal to K. This constant K at point B is equal to P2 V to the power gamma, and this constant K is equal to P3 V3 to the power gamma at point C. We use both these terms. In the first term, where we have V3 to the power 1 minus gamma and it is multiplied by K, here we put the value of K equal to P3 V3 to the power gamma. And in the second term, where we have the term of V2 to the power 1 minus gamma, when it is multiplied by K, here we use value of K as P2 V to the power gamma. This term now becomes 1 upon 1 minus gamma P3 V3 minus P2 V2, and P2 V2 is equal to NR T1. P2 V2 is state P2 V2 is state at point B. Here temperature is T1. So at point B, P2 V2 is equal to nRT1, and P3 V3 is at state at point C. So at point C we have P3 V3 equal to nRT2 from equation of state of ideal gas. So substituting these two values here, we get work done W2 equal to NR upon gamma minus 1 into T1 minus T2. Here we have multiplied by minus 1 in numerator and denominator, so that denominator becomes gamma minus 1, which is positive as gamma is greater than 1. Minus is multiplied in numerator and minus is multiplied also in denominator, and we get work done W2 equal to NR upon gamma minus 1 T1 minus T2. Similarly, for other two processes we can calculate the work done. For process 3 and process 4, that are isothermal compression and adiabatic compression. In these two processes, work is done on the system for first two processes work is done by the system, and for last two processes work is done on the system, because the two processes are compression. So in third process, work done is W3. We must correct it here. W2, in place of W2 we must write work done is W3, and this work done we write as minus integral PdV. Minus sign is introduced because now we are writing W3, which is work done on the system, not work done by the system. So work done on the system W3 equal to minus integral PdV, and limits of V are V3 to V4. This integral can be calculated as we have calculated previously integrals, and it comes out to be equal to nRT1 log V3 upon V4. This is obtained as we obtained this equation for work done W1 equal to nRT1 log V2 upon V1. Now we have W3 equal to nRT1 log V3 upon V4. And here it is not T1, it is T2. Now temperature is T2. So work done is W3, and it is equal to nRT2 log V3 upon V4. And this work done is equal to heat Q2 that is given to this system. Now that is given to this sink. In this third process, the ideal gas, which is working substance, it gives heat to this sink at temperature T2. So this heat Q2 is equal to work W3, and this work W3 is equal to nRT2 log V3 upon V4. Write W3 in place of W2, write T2 in place of T1 in this equation. And similarly in last process, process 4, that is adiabatic compression, we calculate the work done W4, which is equal to minus integral PdV, and now limits are V4 to V1, and it is same as that of work W2, nR upon gamma minus 1 into T1 minus T2. This work W4 is also same. W4 is equal to nR upon gamma minus 1 T1 minus T2. Now total work done in complete cycle, in Carnot cycle, total work done W is equal to W1 plus W2 minus W3 minus W4. First two works W1 and W2 are taken positive because these are work done by the system, and next two works W3 and W4 are taken as negative because these are work done on the system. So work done by the system W is equal to W1 plus W2 minus W3 minus W4. As we have seen W2 equal to W4, so these two terms cancels out, and this becomes equal to W1 minus W3, and W1 is equal to Q1 and W3 is equal to Q2. So total work done in complete cycle in Carnot cycle W comes out to equal to Q1 minus Q2. Q1 is heat taken from the heat source, and Q2 is heat given to the sink, and the difference is equal to the work done in complete Carnot cycle. Now we calculate the efficiency of Carnot engine. Formula for efficiency eta is this. Efficiency eta is equal to work done by working substance, that is W, divided by heat taken by working substance from heat source, that is Q1. So efficiency of Carnot engine eta is equal to W upon Q1. Q1 is heat taken by the substance, working substance, and W is the work done by this. As W equal to Q1 minus Q2, formula for efficiency becomes eta equal to Q1 minus Q2 upon Q1, that is equal to 1 minus Q2 upon Q1. If we put the values of Q1 and Q2, this ratio Q2 upon Q1 becomes this: nRT2 log V3 upon V4 upon nRT1 log V2 upon V1. And we can prove that the values of these logs, log V3 upon V4 and log V2 upon V1, these two values are same. To prove this, we consider two processes, two adiabatic processes in this PV diagram. First is BC and second is DA. These are two adiabatic processes, BC and second is DA. For adiabatic process, we have equation of state. We have used equation of state as PV to the power gamma equal to constant. For adiabatic process, equation of state can also be written as TV to the power gamma minus 1 equal to constant. Now we use this equation of state for adiabatic process. TV to the power gamma minus 1 equal to constant. And we put values of TV to the power gamma minus 1 for point B and C, and similarly we put values of TV to the power gamma minus 1 for points A and D. Point B and C are at endpoints of adiabatic process, and also point D and A are endpoints of adiabatic process. So for these two processes, if we put the value of TV to the power gamma minus 1, we have these two equations. T1 V to the power gamma minus 1 equal to T2 V3 to the power gamma minus 1, and T2 V4 to the power gamma minus 1 equal to T1 V1 की power gamma minus 1. From these equations, we put the values of T1 upon T2, and these two values comes out to be equal to V3 upon V2 to the power gamma minus 1 and V4 upon V1 to the power gamma minus 1. So we have V3 upon V2 equal to V4 upon V1, or V3 upon V4 equal to V2 upon V1. If we put these values in this equation for Q2 upon Q1, we see that the two terms in numerator and denominator, two log terms, log V3 upon V4 and log V2 upon V1 cancel out, NR also cancel out, and we get Q2 upon Q1 equal to T2 upon T1. And efficiency of Carnot engine now becomes 1 minus Q2 upon Q1, that is equal to 1 minus T2 upon T1, that is equal to T1 minus T2 upon T1. It is clear that efficiency of Carnot engine depends on temperatures T1 and T2 only. T1 is the temperature of heat source and T2 is the temperature of sink. So efficiency of Carnot engine depend only on the temperature of source and temperature of sink T1 and T2, and it does not depend on the nature of working substance. Efficiency eta is proportional to temperature difference of source and sink. Efficiency is proportional to T1 minus T2. If T1 minus T2 is large, efficiency is large. Efficiency eta have maximum value 1, that is 100%, if T2 equal to 0 degree Kelvin. Maximum value of efficiency eta will be maximum when T2 is 0, that is source of temperature of sink T2 is 0, but it is not possible. 0 degree Kelvin temperature is not possible. T2 equal to 0 is not possible. So efficiency 100% efficiency is not possible. Efficiency will be always be less than 1 or less than 100%. So Carnot consider an ideal heat engine and prove that even if we take ideal heat engine, its efficiency can never be 100%. It is always less than 100%, less than 1.